Okay, so big thing. So we're going to complete the square. In this one, we have the sum of the length and the width of a rectangle is 20 centimeters. Determine the dimensions that produce the maximum area. If we treat a square like a rectangle, what happens? So first of all, we have the sum of the length and the width of this rectangle is equal to 20 centimeters. This is our first piece of information. Our second piece is that we're looking for the area, which is the length times the width. If we do some substitution, and let's say we're going to make a some function of w, we're going to then have a is equal to, and we want to keep the w's, and we're going to make L, so we're going to make this as let L equal 20 minus w, okay? So basically what that means is that we're going to have this length, we're going to walk this far and then up, and then we're going to have that distance, L and w is 20. We're just going to say that L is this whole distance minus w, right? So if we were to drop this down into a line, we'd have our L and our w. This whole thing is 20. L happens to be this whole distance minus this bit, right? Which is L, because we have L minus w, and that's what, 20 minus w, and that's what we're going to call L. Okay, let's substitute in L in our second formula. So we have our equation 1 and equation 2, and let's substitute 1.5. Let's call this equation 1. 1 and equation 2, and substitute 1 into 2. So we have 20 minus w times w. If we're going to look at this area here, we essentially, if we're going to draw our little box, this is indeed a square, but we're going to treat it like it is a rectangle here. We know it's a square if we really quickly go through. Our area is a, and we're going to have w 20 minus w. Okay, so first off, let's find the roots, right? So if we want to maximize the area, we know that areas are squares, and this is going to turn into be a parabola, right? So if we quickly expand this on this side, w times w, let's go w squared, and then w times 20 is 20w, right? So we know this is going to be a parabola. It's a quadratic equation. We want to know what the vertex is to maximize the area. If we're going to plot it, let's do that down here, right? We know that it's going to look something like this, where we have our area and we have our width, or our w. So we maximize this area. We know that in this case, we're going to find our two roots, and halfway between the two roots is going to be our vertex value of w, right? So our vertex here is going to be some value of w equals h and a equals k, right? So this point here is going to be hk, which is our vertex, okay? And so to maximize that, we can find this point here, which is when w equals h, and that's straight in the middle because parabolas are always perfectly symmetrical. Okay, so a, when it's maximized, we can find halfway between the two roots, right? We'll find that h value and then see what happens. So what is the first root, right? So the first root, we can look straight into this area here. What makes this 0? Well, when w equals 0. So root 1 when w equals 0, and 2 when w equals 20, right? So 20 minus 20 equals 0. That's when the area is 0, or when we're on the y-axis is 0, or when the parabola intersects the x-axis. Okay, so what's halfway between 20? So we know this value here is 20, and this value here is 0. Halfway between there is when w equals 10, right? So when w is 10, we have a maximum area. And if we go back to our original question here, we have L equals 20 minus w. Well, I know that w is 10, right? So we know that, let's just do it right here. L equals 20 minus w. L equals 20 minus, well, what's our maximum, right? We want the maximum value at w equals 10. So our L value at maximum is 20 minus 10 equals 10. So we know it's a square. We know that the area is 100, and it's done so by a length of 10 by a width of 10. Okay? So we're going to treat this like a rectangle instead of a square. So we already know what the answer is. We know that it's 100, right? We know the maximum area that we can get is 100. If you were to go through every value of W and L, right, make little slivers, so 19 and 1 and 18 and 2, if you made a table of all the possible rectangles that we have that add those lengths and the widths to 20, and then you plotted them, you would plot this parabola. We're going to have our area, which is equal to this algebraic expression, and let's just stick with this one right here, number 3. Because we know that this is going to be W, and then we have 20 minus W to make up that square. So this area is the same as this area here. So these two areas are exactly the same. Okay, they don't look it, but let's imagine. We have a little bit of scaling. Okay. So we know it's a square. We're going to pretend it's a rectangle the way we drew it up top. Let's say we wanted to complete the square, right? Which is of the form, let's say x squared plus bx equals the area. If we were to quickly do this, we know that this would be our x and our x, and then we'd have plus, we have our b value times our x, right? And so this is equal to our area A. And so what we're going to do to complete the squares, we want to make these two things, because we know this is a rectangle, right? If we put them together, then real quick, let's draw that out. We have our x and our x plus b, right? Equals A, okay? So what we're doing now is we're just splitting these up. We're splitting it up here, and that's where we go this way. Okay, so we've got our x. So after we split it up, x times x, and then we split our b and our x. What we can do is we can stick this side x right there, right? This length is the same as that length. And then we can split this in half, split that in half, and then swing that over and put it underneath, right? So if I split this in half with my math scissors, essentially what we're gonna have is we're gonna have this square, and we're gonna have these guys just sitting right on top. And let's do it the other way. This guy's gonna get stuck here, because let's do it down at the bottom. Shall we? There. And this is gonna go right there. So this is x, and that's x, that's x, that's x, right? All these side lengths here are all x's. This bit's a b, and this bit's a b, okay? So we have this x squared, and then we have this bx and this bx area, okay? So to complete the square is to take this extra little bit here, which actually isn't a, because this bit with the space missing, this is equal to a. It's so much easier to go x plus b times x plus b, okay? So it's a lot easier for us to go x plus b times x plus b, right? Plus b squared, that equals a, right? So that's a heck of a lot easier. And in order to do that, we need to figure out what's this size. Well, the size of this thing is, oh my goodness, big mistake, divide by 2. We're taking this b, right, and we're splitting it in half. Oh my goodness. We split that in half, right? That's how we made it. My goodness. So we take this b divided by 2. Whoa. Everyone makes mistakes. Nobody's perfect. And we take this b divided by 2. B divided by 2. Okay. Crazy. Okay. So it's a lot easier to say this divided by 2, right? This is equal to that. But it isn't, because there's actually this space missing here. And this space is the area of b divided by 2 squared, right? That's the missing area. So if I would like to say x plus b squared, I have to add this b over 2 squared area to that value. However, I then have to subtract it from the actual area. So I have to do this to both sides. We're adding a fancy 0. I got to take that away from our area, our big area, the one that it already is, minus b over 2, and we're subtracting that area from the other area. Okay, So this number is really how we complete the square, right? And so then we'll bring it back over, b over 2 squared plus b over 2 squared equals a. Okay, there we go. And this essentially is our vertex form, right? Right, and this is what we look at right there. Okay, so we're gonna flip over. And so now we know kind of what completing the square is. Let's try to do this with the rectangle that we had. We're going to do this with the rectangle that we had. So we started out with this w and then 20 minus w. I'm going to rewrite stuff right here. Okay, so right now we have written down equation number 3 from our area equation. This is where things get really interesting. So we have this 20 minus w term on the top here. We get this 20 minus w term. So let's think about this. So we've got 20. So we got w here, and that's fine. So let's take w and let's actually make 20. Okay. So we have our w. Yeah, we have our w and our 20. And so what we're going to do is I'm going to take away, because if we do this here, if we put this all in, right, we get minus w squared plus 20w, right? So if we've got our 20w, which is this rectangle right here, we got our 20 and our w, this is that one. And we're going to subtract out a w squared here. So essentially, we're taking this away. Well, what's this side length now? Well, that's this side length here is this full 20, and you've taken away a side length of w, right? So this is what we got with the 20 minus w. And so that's kind of how we're getting this, right? So if you expand it, really what you're doing is you're adding this up and then taking it right away, right? But you're saying that, right? So you're saying that you're adding this 20 and then taking it away. Or you can just say, hey, I got this rectangle that's this side lengths, right? But you lose that negative, which is subtly important. So if we're going to traditionally complete this square, let's assume that w is pretty small, okay, compared to, let's say, 20. So that means, let's say w is like 2 or 1, 20 minus 1 is 19, right? So this is a lot skinnier than you think. It's a very extreme rectangle. So that when I draw something like a square inside of this area, our w and our w, right? And then we have this, our old rectangle, this whole side is 20 minus w, right? Now I'm just taking this little square inside. What's this side length now? The new one. Well, that's our original side length minus another w, right? This 20, and we're just taking, this is just that length minus another w. So we're going to take 20 minus w, right? So that's our new side length, okay? Stay with me. If we do that, then what we have really is we have 20 minus 2 w's, right? Times w. And then we have this w squared here. Okay, so we've got our 2 added now together. We have our, just like before, w squared, and we have our 20 minus 2w times w square, right? And we're going to add those together. So if we're going to complete the square, what we generally do is we cut this in half. We can do just a quick factoring of the 2, right? And this is a little enlightening. It's because if we have this factor of 2, we have 2 times 10 minus w. And if you remember, w was 10, right? Because the overall area was 100, and L and W were both 10. So what we're doing when we're adding this second square is we're adding a 0, because this W is 0. It's 2, 10 minus 10 is 0. So this is 0, right? But we're pretending it's not. So if we were going to split this in half, okay, well, we're splitting this side length in half because we want the W to stick to the W. So we're splitting this in half. And we know that this is factored already by 2, so we're dividing this by 2. Okay, so we have got our 2, 10 minus W, which is equal to our side length. Okay, because we just factored it. We're just going to divide this by 2. So we have our 10 minus W. This side length here becomes 10 minus W. Okay, so we're gonna put on our, stick that there. No, I did that last time. Stick that there, stick that there. Okay, so now we have our 10 minus w and our 10 minus w, right? And then we're looking for this thing. Now here's kind of the problem. We can look, and again, here's another huge clue, is if we try to do this, we have our, okay, so we have our 10 minus w and 10 minus w and w. Okay, well, what happens if we just, what's this side length now? This big one, right? Well, if we add them together, right, because we're going this distance and then this distance, we have our w plus our 10 minus w. Well, what does that give us? It gives us 10. Boom, we have 10. Boom, we have 10. Okay, well, what's this area now? It already is a perfect square. We've already completed the square. 10 times 10 equals 100. Okay? However, new page. So if we go back, so we're just going to redraw that. So if we are going to complete the square, what's this value? Right? Okay, well this is this length and this length, these 10 minus w's, right? That's this times this. Well, that square is 10 minus w times 10 minus w, right? And then we got 10 minus w squared. Excellent. Let's expand that, shall we? Okay, so we've got w squared minus 10w plus 100. W squared minus 20w plus 100. So if we go back to our original question again, so we have this is our new square, right? It really doesn't help us solving anything. We didn't get to our vertex form or anything by adding this term. If anything, we've conflated the entire issue because we're pretending that it's a rectangle when it's not. And here's the reason why, is if we go back to the beginning and we have our area equals 20 minus w times w. There we go. Okay, is our minus w squared plus 20w. If we look, if we make these are the same, so this is our area, right? This is the area that we're looking for. If we compare that to this new square, if we compare that, and let's make it so that this is the same. So let's substitute in, let's get this and substitute in the value, right? So if we've got our minus w squared, or sorry, let's start there. W squared minus 20w. So if we want to take the negative of this, right? So let's take the negative of that. And then we look at our minus 100 now, right? So we just took the negative of this whole thing. If this is 0, which we can assume it is, based off of kind of our testing, that means that I have minus w squared, factor in the negative 1, plus 20w equals, right, let's add 100 to both sides, okay, so is 100. So from completing the square, if, which it now has to be true, because now I have the same, these are the same now, right? This is our area, is minus w squared plus 20w. Therefore, this term here must be 0. So not only have we kind of concluded from like previous analysis that that w is 10 and that 10 minus 10 is 0, right? So we already knew that. But this definitively shows that this initially was a rectangle, and we've done that algebraically.
Initially was a rectangle.
What?
Rectangle.
What the fuck?
The area is 100. Because if the right side equals the left side in this equation, our area is 100, which from previous analysis is for sure 100. And that's the weirdness that happens when you pretend things exist. So that's kind of the result if you pretend that a rectangle is a square. Okay, see you in the next one.